and whether or not AI and religion are compatible. So
Excuse me,
interesting.
Phil, are you with NASA?
No, I'm retired.
Oh, okay, because I'm a brand new member, so I don't
Okay.
know very many people yet.
Well, welcome. My background, I was with GE Lockheed for quite a few years, and I retired in 2012. And we
Okay.
just recently moved to a retirement community in Lancaster, Pennsylvania. So I used to be active, but now I can't be very
You need a
active.
membership thing. I can't take your check until you get a form.
How about yourself?
I'm retired as well. I
Then you would mail it
was
to me as a check.
a journalist and a writer during my career.
Oh, okay.
Also worked a little bit many years ago in TV and radio.
Oh, that's interesting.
But my interest in astronomy is relatively recent. So I've got a lot of catching up to do before the time clock runs out on the game here.
Don't worry, you'll have time.
Never too late.
There are 5 minutes left in the fourth quarter, and I'm out of timeouts. So
I still have 3 telescopes, but nobody to share the experience with, since you guys are all the way over there.
What about the opportunities for pretty dark skies out in
Not where I live. I'm right next to a shopping mall.
Oh, okay.
So that's not so good. If I want to see dark skies, I got to do pretty much what Chester County Astronomy Group does. Go for a ride somewhere and out into the country.
So where's the shopping mall exactly?
Well, it's Harrisburg Pike and Route 30, right on the corner there.
Oh, okay.
So we're in Amish country over here.
Sure.
It's a nice place.
My wife and I like to visit whenever we can, and we've often had lunch at a little restaurant called Yoder's out there, which is not too far from this big place called Shady Maple.
I know where that is.
Yeah, that's a huge tourist attraction, and for locals too. Yeah, they do a heck of a business there.
Yeah, and they've got an excellent shopping market there. You can get some really good prices on some really good food.
Yeah.
But yeah, now, and Yoder's is not too far from me either.
Oh,
Well,
okay.
if you ever decide to take a ride out there, give me a jingle. And I'll be happy to meet you and chew the fat about astronomy. Do you have a
that'd be great.
telescope?
That'd be great.
Yeah. Well, like I said, you said you're just starting. Actually, I started many years ago, but I stopped. And so I haven't used my telescopes in a long time.
Oh, okay.
I've taught a 10-week course in interstellar space travel. And that was fun. I enjoyed doing that at Immaculata University.
Oh, sure. Yeah.
Summer. The senior program.
Okay.
In fact, I lectured a number of times here at the Chester County Astronomical Association.
Okay.
So, but I get rusty. My brain is not as powerful as it once was, but I try to keep it oiled every now and then.
Yeah.
That's part of why I'm here. I'm oiling the gears.
Sure. You got to keep them greased, brother.
That's right. That's right.
Absolutely.
Now, tell me you mentioned you were doing some work involving AI and religion.
Yeah.
I'm just curious, who are you working with on that?
I'm not. It's not working with. I started a group here called the Change Navigators, and what we're doing is we're investigating AI, quantum physics, quantum computers, neural networks, virtual reality. And we meet once a month and we talk about these technologies and how they affect us and will affect us or we affect them. And how right now I'm looking at religion and artificial intelligence and how they relate to each other. I have a very religious community here. A lot of Mennonites, and Amish. And so AI is, so I'm trying to show them that indeed artificial intelligence is compatible religion.
That's very interesting. How is that message being received by those communities?
Good question.
So far, so good.
Well, that's
I mean,
great.
I've pretty much gone into how it affects or is going to affect our lives. So I've shown them different things about AI and how it will replace a lot of jobs, things like that.
Yeah, sure.
But yeah, it's AI is unbelievable in many respects.
Oh yeah, yeah.
I know when I worked in AI for 12 years, but that was before it took off like it has. I'm retired since 2012. So that's in that time, it's unbelievable how it's changed.
Yeah. Well, the Amish folks that you talk to, given the restrictions they have on modern technology, have they gradually adopted anything that would allow them to see AI at work in their own homes?
Well, I actually talk mostly with Mennonites.
Okay.
Mennonites, okay.
AI, Amish are in the community, but I don't think I have anyone in my group who's an Amish person.
Okay.
I'm curious about how people view AI, especially when we talk about Ray Kurzweil and transcendence. Okay, the merging of artificial intelligence with humans' intelligence. So it's exciting.
Oh, it is. It is
Exciting,
for sure.
exciting, a bit scary.
Oh yeah, yeah.
Yeah, like I said, a lot of people are worried about AI taking over the world. Well, AI is us. We program it with all our prejudices.
Yeah, sure.
It's
Well, I'm
very
sure
true.
that people who are in the who are moral theologians as well as metaphysicians are really interested in this.
I would bet they are. Well, I'm
Yeah.
hoping. I'm hoping they're interested.
Have to repeat it.
I'm interested.
There's a guy, I can't think of his name at the moment, but there's a guy at Cambridge University in the UK who has written a lot about the intersection of religion and science
Down to my
over the
seat.
last probably 35 years he's been writing. He's an Anglican
Sometimes the
priest
dog starts
by
barking.
training.
I understand.
And he's taught at Cambridge and written a lot of books about that subject. And I don't know if he's tackling AI.
And you know how to share all that stuff, right?
He's not a young academic anymore, so I don't know how active he is in producing papers and stuff. But
Yeah, I wish I was either this technology had started 10 years ago when I retired, actually 20 years ago, I would say.
yeah,
When I could have been part of it. Now all I can do is sit on the sidelines.
sure.
But I'm thankful there's sidelines to sit on,
Yeah, yes, that's right. That's
like
right.
this one.
Always could be worse. Yeah.
Oh, yeah, absolutely.
Yeah, we don't do this. Started zooming.
So what brought you to the group, Stephen?
And then,
Well, it's kind of a long story. Over the years, I've read some Greek and Roman history and their interest in the stars and of course the constellations and how they came to get named and how the roles they played in in the cultures of those two ancient
I said it there.
countries and city, Athens and Rome. So so I kind of got interested in that first, and then just in the past year or so, I just started reading more and more about the advances that have been made in telescopes. Makes it somewhat easier for people with no experience to get into the pastime and to learn about it relatively quickly. So that kind of drew me a little bit. So I've been, reading up on things in the past, 6 to 10 months, and finally decided to join this group because it was near my home, but also because I live in Delaware, in Western Delaware County. So there's many chances for good viewing opportunities here.
Oh, yes. This Chester County Astronomical Association, do they sponsor classes in telescope usage?
Yeah,
Wow.
we have, there's a night through the night school. And
Okay.
I think it's called adult learning now. It used to be called Chester County Night School. I forget what
Mhm.
it changed to. Our group gives classes that they're going on now, as a matter of fact, and one of the
Mhm.
classes is about telescopes.
Ah, okay.
Yeah, so one of the classes about the sun, one's about constellations, the moon, stuff like really primary, like primer type of things. But one is observing and telescope use. So
Excellent.
it used to be done by Dave Hockenberry. I don't know if he's still doing it, but we established these classes
Mm.
and quite a number of years ago.
Well, also a member in the Delaware Valley Astronomical Association, and they do have classes on how to use telescopes. In fact, one is going on right now.
Oh, okay.
So if you want to check there too, that's another resource.
In fact, it's interesting. I was exchanging emails with Don Knob just last week,
Mhm.
and he had mentioned that he's a member of that organization,
Yeah.
and so I looked into it, and I literally just joined it on Saturday.
The
Okay.
DVAI?
Yeah,
Oh, yeah,
yeah,
it's a
and
good
so
group.
I don't know anybody there yet, but I will. I hope in the next few months to get to know some of those people as well.
Yeah, I think the one thing I might add is, unless they've changed immensely, this group is filled with a bunch of people who care about each other, and you can feel very much part of the group. Some AI groups, they're off in their own world,
Yeah.
but this one that we're on now is very full of great people. They have a breakfast once a month. I think Dave. No, it isn't Dave. Who's the guy who orchestrates?
Frank.
Frank. Oh yeah, my friend Frank. He's also a member of my um, happy hour group.
Oh,
I,
good.
in fact, I bought a telescope for him. I gave him two of my paintings, and he gave me a Cassegrain telescope. So I'm happy with that.
That's
Wow,
nice.
nice.
Yeah.
Yeah, well, it's the thing with the Cassegrain, it sits on my table, so I can easily move around. My Newtonian is too big to fit on board because I don't have access to a yard, but I've got a very nice patio in the back of my apartment, and I can set it up there and look.
One thing our group does a lot is outreach. Scouting groups and
Mhm.
local community groups and that kind of thing. So yeah, we started doing that many years ago.
Yeah, no, it's a great group. I really
Yeah.
really love it. I wish I didn't have to move. But on the other hand, I've reached a point in my life where as you can probably see, I am on oxygen therapy. I have difficulty breathing, so I couldn't upkeep a house anymore. So a retirement community was my way to help me, and then also give my wife access to all sorts of people over here. She's my socialite.
Are you enjoying it so far? The place where you're
Yes, in many respects, I am. I wish I had people who taught scientifically. That's why I started this Change Navigators group. It's a very, very much more religious oriented group. The home that I'm in is sponsored by the Mennonites. And so there's a lot of Bible studies and stuff like that, which I'm a member of too. But I don't know. I got this yen to how would I say, to talk astronomy and AI and virtual reality, and not just the Bible.
right? Yeah, right.
Yeah, I'm actually working on an interesting painting now too. It's Jesus on the moon. Hey, let me show it to you. Hold on.
Yeah.
Let's see. Hold on. No, I don't want to blur background. Hold on. Okay, there we go. Let's see. Did I get rid of it? I guess I did.
Hi, Susan.
I gotta get it
Hi, how are you?
off my
Good.
easel.
We saw you pop in.
There we
Yeah.
go.
I'm in the
Ah.
middle. I just got home. I'm eating dinner, so I figure I'll take my
So that's the
video
Honey,
off.
during the talk.
that's the painting I'm working on now.
Oh, nice.
That's
Oh, very nice.
Jesus on the moon.
Jesus on the moon. That's basically I was thinking that our world is in such a screwy mess nowadays that you know, Jesus walking on water and he saved the disciples in the boat that was going to sink. So here we see the earth going to sink and Jesus comes to save us. So I decided I'd paint it. So I did it from, you know, rain. And so it's a little, I had a little trouble with the moon since I never been on it personally. But still, it was interesting.
Oh,
I'm mainly a tall ship artist.
oh, okay.
Yeah, I do tall ships and portraits, things like that.
Oh, nice. Very nice.
Yeah. So I got a few hobbies to keep me busy here.
Well,
Here
it sounds
in
like it. Yeah.
retirement community.
Yeah.
Actually, the lady sitting next to Barb, she can go it's just so.
Great, just keep coming, you know?
So she joined. The guy back there, Christian, he just joined tonight. So, yeah. and
What's the membership up to now, Don?
Excellent.
Don, what's the membership up to? Hey, Don, can you hear me?
Yeah, I can hear you, yeah.
What's the membership up to?
177.
Wow,
Out. Wow.
really? Did they all show up?
God, no.
Not all.
It might be something, huh? If they did. Oh, you had a pretty good turnout here. Yeah, very nice. I wish I could come. Hey, there he is. How are you? Ah,
Hey, Donnie, we're up on Zoom and YouTube?
Yep.
Okay.
I can't believe how we're
Way to go.
changing.
Yep, I think they see. Say
Save
something,
me,
see if they can hear
save
you.
me some coffee there.
Are we up, running? Everybody out there in Cyberland, hearing us okay?
Yes.
Yeah.
Yep.
We're
Okay.
here.
Welcome everybody to our last meeting for 2024 of our regular meetings here in Westchester. It's something I want to also, it's in the newsletter, but I want to re-emphasize it again. Next month, we do not have a regular meeting. We have something, we have a party. Our holiday party will be at Iron Hill Brewery in Westchester on Gay Street. And I think we're starting at about 6 o'clock. So, please bring yourself, family, friends, whatever. Just come on. It's going to be a great time. The format will be the same one we've been using for the last couple of years, as the club will pick up a few appetizers to put out for everybody, but your drinks and your dinner on you. Usually they like to put us in what they call the bullpen, which is that area in the back of the restaurant where it's sort of like a long corridor kind of shaped room where we can sort of be out of the noise and the hubbub of the rest of it. We can create our own noise and hubbub while we're out there.
And we should tell people, we announce with email to bring cash, because they give us one bill, so you gotta be able to pay your bill in cash.
Yes, when they have that many people, it gets really overwhelming for the poor waitresses to make separate checks for everybody. So either bring cash or whatever. If it's a check, Don will throw it on the floor and see if it bounces. But whatever it is, we're gonna be paying this sort of out of one fund or one credit card. So whoever's handling that's gonna have to be in person. And last year, it wasn't,
It was you, I think.
it was me, I think. So, please, no rubber checks, but cash is the easiest to do, because then we can also, put a nice tip in there for the folks that won't be taxed by Uncle Sam. I'd like to give a shout out to everybody that helped us with the helicopter museum, event that we did. It was a busy event. We were mobbed, but yeah, it came off fantastically. A special shout out to whoever was manning that poor desk inside the museum because they were swamped too. But we had a lot of folks there. I think we got 2 or 3 members, family memberships, just from that alone. And the folks there were very appreciative of all of our efforts for showing the people the night sky. They've already talked about having us back again. I think they want to do 2 or 3 events next year. While we're on that subject, I would also like to put a special shout out to one of our members tonight, Mike Manningley, who has been our program chair and is now yielding up the chair to whoever would like to take the job. Don Miller is temporarily doing it sort of just for now, but we are looking for a permanent observing chair. And it's an important job. You don't have to do anything with a telescope if you don't want to. But how that operates in the club is that these people take the request from the public for to have them do sky events. Girl Scout and Boy Scout, for their badges, their astronomy badges from municipalities, Parks and Recreations Department that want to have us put on an event for them. You coordinate with them and get dates on the books. And Mike's done a fantastic job for us. It's not the easiest job in the world because I'd say that about half of the events that we're scheduled to do wind up getting clouded or rained out. But it's an important job, and anybody that's even remotely interested in the job, please see me or Don Nab or Don Miller or Mike, and we'll get you up to speed on what's involved in the job. We'd really like to have somebody take that position. And other than that, I don't think I have a whole lot else to add. But just again, thank you for all the people that showed up with telescopes for the helicopter museum. That was an extraordinary event. And now I'd like to turn it over to Don.
I have nothing really. Let's let Bruce introduce our.
All right, Bruce, you're on.
Wow, that was easy. So, hi, everyone. It's a real privilege to introduce our speaker tonight. It's Ronnie Sheff, the professor and the graduate chairperson in the Department of Physics and Astronomy at the University of Pennsylvania. I'll give you 1 or 2 sentences of what Robbie works on, because beyond that, I need to get a PhD in astronomy just to explain what he works on, because that's how complicated it is. But basically, he is a pretty world-renowned astrophysicist and cosmologist. And we've had him talk here before. I've had him speak for local chapters of the Planetary Society as well. Basically, Robbie focuses on stochastic processes in developing physical models and statistical methods to really look at data from large-scale galaxy formation studies and cluster surveys to sort of constrain or understand models of galaxy formation and really to, I would say, refine our understanding of cosmology, the Hubble constant, for example. But tonight, he's going to talk about something a little different, and it's making black holes out of light. So if this presentation is anywhere near as intriguing and informative as the one he gave several years ago on gravity waves, I think we're all in for a very good surprise. So, Robbie, thank you so much for coming. Appreciate it.
Thanks. Thanks very much for having me back. It's humbling to hear all the stuff you guys are doing to reach the broader community. So, like Bruce said, should I? Is it better if I'm up on?
You know, you can come up here. Sure, it's up to you.
So, like Bruce said, I mainly do stuff. You can walk over the station. I mainly do stuff that is cosmology. So for me, galaxies are dots. So stars are even tinier dots. And I mainly try to figure out from the distribution of light that we see, what the distribution of all the stuff must be. So think of it as you see the tip of the iceberg, you want to figure out what the shape of the iceberg is on. So that's mainly what I do. And in the course of doing this, I sort of made models for how gravity pulls stuff together, and makes big groups of galaxies. And So I sort of, my stochastic models were trying to describe how many big guys and how many little guys you're gonna make, a lot more little guys than big guys. And I did that for quite a few years. And then just before COVID, just before the pandemic, someone came to talk to me and they said, well, you know, I'm interested in much, much smaller things than galaxies or stars. I'm interested in tiny black holes. Okay. And so so they were interested in figuring out how many tiny black holes there might be in the universe. And so let me try and set up the problem first. And then I'll try to set up why this is such a weird thing to be looking at, but you'll see that there's many cool things that are a consequence of this one key idea that goes about it. I'll give you the idea. So the background is a little bit that when we try to understand what the universe is like and why galaxies manage to pull themselves together, because the universe is expanding and gravity is pulling stuff together, why that happened, then we quickly find that there must be a lot of stuff in the universe that didn't make light. So a lot of stuff that makes gravity, but it doesn't make light, right? So we call that dark matter. And that's kind of what I'm saying here is, what's the matter is a little bit of play on what's the dark matter. And we're going to talk about the matter. For most people, the matter is a new form of matter, like a new particle. And so for the last 50 years or so, we've been looking for the dark matter particle. So one option is a neutrino, right? And you guys will be hearing about neutrinos in a couple of months. So that was one candidate for what the dark matter might be. And it's because that's a particle that doesn't make light. We no longer think that there are enough to be the dark. So it's got to be something. But we don't really know what to look for. So people have been looking for their favorite kinds of things, but it's a bit like you don't know what you're looking for. You look under the light, under the street light, and then you're not going to look somewhere else where it's harder to look. And so if you don't find something under the street light, then what do you do? And so for 50 years, we've looked and not seen it. There's a couple of clever ideas about why we might not have seen it. One clever idea is, well, we're looking for a particle. And so a particle means something small and you know where it is. And that's different from a wave. Yeah, and so we're used so we're used to thinking that light is like a wave. Okay? Light happens also to be like a particle. Okay? And so light is this funny thing that can be either thought of as a wave or as a particle. And so people have started thinking maybe particles can also be thought of as being waves. And the way the analogy goes is if something is like an X-ray, so an X-ray is a wave that's super short, and a radio wave is something that's super long. And so a particle it's like very condensed energy. And so it's got a really short wave. And so people think of particles, if they're going to think of them as being waves, as being things with very short waves. But if a particle is really light, because Einstein said E equals mc squared, so if the m is really small, then the energy is very small and the wave can be a long wave. And we usually think long like radio waves, long. But people said, let's go crazy, because we don't know what the dark matter is. What if the particle is tiny, 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 like not an electron, like a billionth of an electron. Tiny, tiny. If it's that tiny, then you can ask, well, then the wavelength is long. How long? As long as our solar system. As long as the spaces between the stars. As long as our galaxy. And so that's the direction they've gone, right? They've gone to the direction, they've gone to say, what if the dark matter particle is so tiny that if you thought of it as a wave, it's as big as our galaxy. It's the wave is as long as our galaxy. It's a very weak wave, but very long. And if it's very long, then any experiment we do here on Earth to detect a particle, we won't see anything. Because it's a wave. It's like a fluid. And so maybe that's why in 50 years, we haven't seen a particle. We haven't seen the dark matter. Yeah, because it might not be a particle at all. Okay. So that was a pretty long introduction to say we really don't know what light to be looking at, right? Should we be looking for a particle or should we be looking for a really, really low mass particle that's better thought of as a fluid? And we should think of it as a fluid because now if I have two particles, but they're each like really long wavelengths, then the wavelengths overlap with one another. And that's what we think of as a wave fluid. Yeah. So that's why we'd say the dark matter is then a fluid. It's very low mass. But we have no idea. And so this, what's the matter with primordial black hole? I like this idea because, well, maybe because it's a street light, I understand, right? It's saying maybe the dark matter is not a new kind of particle. Maybe the dark matter is just black holes. And we know that black holes could exist. So you don't have to make up anything new. What you do have to make up new is how are you going to make enough black holes? Like how did we not notice, right, if the dark matter is made of black holes? And so how have they stayed hidden for this long? And how will we figure out that they're there? Right? So those are the two questions. Right? So what's the matter with primordial black holes is sort of asking that question. And there's a key word in there, which is, it didn't say what's the matter with black holes. It said, what's the matter with primordial black holes? And so the primordial here is saying that these are black holes that are not made in the way we know how to make that black. So how do we know how to, yeah.
So what about the Hawking's radiation, and wouldn't these have evaporated in this amount of time?
Totally. So we're gonna talk about that.
Okay.
Yeah. So that's a good question. Did this question make sense to most of you? Yeah. No, to some of you, not to everyone. Okay. So we'll go through this, right? So the idea is going to be, let's make these a long time ago, and if we made them a long time ago, we got to make sure that they're still around today. Okay. So the primordial is they were made a long time ago. In particular, they were made before stars were. Because the main way we know how to make black holes is from stars, from stellar evolution. But these guys were made before that. And there's a very specific thing that makes them, right? And that's the top part of the title. The black holes were made of light. They're not made of starlight. They were not stars that turned into black holes, but made beams of light. So we get it. Right. So no, but I can use the arrow. Yeah. Oh. Yeah. Let's see.
try another share.
Right.
Oh, okay. I'm going to close all the PowerPoints. Start again.
What happened?
Let me try to share again.
Okay.
I'm going to see my PowerPoint open. Slideshow. From beginning. Now try that.
Brilliant.
Gone.
That's what we ought to do. Perfect. Thanks. Okay. So I have a few slides first on setting up why we think we need documents. Guys are ready. Yeah. I should turn this down. Okay.
There we go.
All right, there we go.
That way.
All right, so can I get a feel for how many people know why we think there's dark matter? About half of you. Okay, so I'll go a little quick on this. And so the idea is that when we look at stars that are going around a galaxy, then what we see, so we can measure how quickly they're going around. And by measuring how quickly they're going around, we can ask, all right. So we can ask, as they're going around, what's holding them in place? And so what's holding them in place is gravity, right? And so by measuring how quickly they go, we can measure how much mass is hanging on to them. Right? Because if they were going faster, then more mass is needed to hang on to them. Otherwise, they would fly away. And so one of the things we can do is we can look at a galaxy, and we can say, well, I see a lot of light, and supposing this light is made up of stars that are kind of like the sun. So then I can just add up all the light, say that much light times how much mass, the factor that I need to convert light into mass for the sun, I do that for this. Right? So I'll know that there's 10 billion suns there. But I can also see that there's more light here than there is out here. And so that means that I know that if it's true that the light is telling me where the mass is, then I can make this into a map of, as I go further and further out, I'm getting a little more mass, a little more mass, a little more mass. And I can ask how quickly should things be going around and not escape because of that mass. And so if you used the light to predict how quickly things are going before they escape, then you get this red curve. That the further out you go, they shouldn't be going super fast. And that's a little bit like in our solar system. In our solar system, all the mass is in the sun. And Mercury is going around fast, and Earth is going around not so fast, and Jupiter is going around slower. Okay, so that's when you're far away from the sun, there's like a spike. When you're far away, you go slow, but as you're closer, you're going fast. If all the mass is in the middle. But if the mass is spread out, then it can stay constant. And so when we make the measurements of how quickly the stars are going around the center of this galaxy, and of any galaxy, then what we find is that the speeds never really decrease, which means there's more and more mass in the outskirts than there is light. And so we say there must be a lot of dark matter to keep those, to hang on to those stars. So that's the argument, that there's a lot of dark matter. Okay. There are others, but this is a pretty good one. And it's important that there are others, but it's important that the others say that there's the same amount of dark matter as we think from here, meaning we're missing a bunch of stuff. We can estimate from how wrongly the light predicted how much stuff there is. From measuring this difference, we know how much mass is dark. And there are many different ways of estimating that, not just this, and we all get the same answer. So it's kind of reassuring to know that you're really wrong. So that's the main problem that we have at the moment, is understanding what this might be. And like I said, right, we have no clue. It could be really massive things. It could be tiny, tiny mass. Okay. But we do think that we need the dark matter to explain how galaxies work, and how the universe expands. Yeah. So, could the dark matter be black holes? Right? So could be, right? Because for sure they exist. And we've seen them collide. Okay. So if you want, when I talked about gravity waves the last time I was here, that was this, right? That the black holes collided and they made the gravity waves. So we know it happened. So then, are they the dark matter? But for them to be the dark matter, there's got to be lots of them. So for lots of them, that means, well, we should measure lots of those gravity waves. And now that we have the technology, and the beautiful thing is, since I was here, whatever, before COVID, that was when we were first beginning to detect gravity waves. Now it's one a week, right? That was one in a gazillion years, if you count from when we are looking at the sky, but let's say 1 in 50 that we were funding gravity wave research, right? But now it's one a week, and it's just going to ramp up from there, right? So this is really a big change. But even 1 a week is not enough to explain those black holes as being the dark matter. There's just not enough of them. And so we need to find other ways for looking for black holes that are not the big ones that made those gravity. Okay, so they're smaller black holes. And they're hard to see, right? Because they're not making light. And so we either have to see them in gravity waves, but we could see them in gravity waves if they were pretty massive, because then they make a gravity wave that we can see. The smaller mass they are, the smaller the gravity wave signal, so we can't do that, or not yet, right? And so we need to find another way to see something that doesn't make light. And so one way we do that is with this effect that's called gravitational lensing, which is, if there's a star here and you're looking over here, so the light has to get from it to you, then if there's something massive, and we're going to call that thing a black hole, but it needn't be a black hole. Anything that's massive is going to bend the space around it. And what that's going to do is it's going to mean that light coming to you doesn't come straight to you, right? So if this were totally flat, then the light from here would go like this in a straight line, or like this in a straight line, or like this in a straight line. But now, because this thing is here, the light comes in a wonky pattern to get to you. And you think light travels in a straight line. And so you say, oh, the light came to me from this direction, right? It came like this and came from this direction. So I'm going to point back and I'm going to say, that's where I think the light started from. And so you're going to be wrong about where it started from.
Watch this.
But that's okay. Yeah. So So that's the first idea, is that if you have something massive, it's going to kind of bend the path that light takes to get to you. But supposing I thought about light, that instead of coming this way, went this way. So if it was, far enough away, it would go like that. But supposing the light came down here and then down and then back up, maybe it would, maybe it would bend around almost like a golf ball. Maybe it would bend around this way and come to me from the other side rather than from this side. So if that happened, then I'd see light coming from one side and I'd see light coming from the other side. I'd say, oh, the light came from here, but the light also came from here, because I think light line, I'll say it came from there. And so I would literally see two pictures of the thing, right? I would see it over there and I would see it over there, because the light came from there and the light came from there. And I could check, I could measure the light, I could measure its spectrum, and I could see that this one was identical to that one. I got two images of the same thing. So here's the sort of diagram showing that, right? So there's the light. The light is coming to me. There's a massive thing here that's making the light bend. So instead of coming straight to me, which is what it would have done if there wasn't this thing here, right? If this wasn't this thing here, I would have seen it here. I would have got the right position. The light wouldn't have bent. Because this thing is here, light that would not have got to me, because this thing is here, that light now gets bent and I see it. And I think it came from here. But there's other light that would not have got to me, but because this thing is here, it gets bent and I see it and I think, oh, it started out from here. So I see two images of the same thing. Okay. So we call that gravitational lensing. This was something Einstein knew should happen and thought that we would never see it. But in the 60s, we started to see it. Okay? Here's a pretty dramatic version of that happening. So imagine that you have something massive and we're watching as, so here we kind of have, it looks like there's a galaxy that's coming sweeping through this way, but you should imagine that really what's happening is we're looking at a galaxy and the star came by. And as the star came by, there was a period where it was perfectly lined up with the galaxy that you were looking at. And if it's perfectly lined up, then one of the things that's going to happen is that it's sending light to you. The light's going to go, so before I said it could go this way or it could go this way. So you'll see two images. But if it's perfectly lined up, it could go this way. It could go this way. Go anywhere. And they'll all get to you. And so when everything is perfectly lined up, you see a circle of all the different paths the light could have taken and still get to you, because it's perfectly lined up. And so that's the kind of thing you're seeing. It gets perfectly lined up, and then you see the circle, and then they're not perfectly lined up anymore. And so you see something more complex. Okay? And so that thing is called, that circle is called an Einstein ring, because he realized, there'd be this super special shape every now and then. It'd be super rare, right? It has to be very perfectly lined up. Okay, so the kinds of things that you'll see will look like that, right? When the light is far away, when things are not very lined up, then there's not much distortion. Then as they start being lined up, you start seeing the light can start coming to you from two different paths, and then from multiple different paths, so that you get the full circle, and then they're not lined up again, and it goes back to being just two. Okay? All right. So now suppose that, suppose that these two images, or the full circle, supposing it's really tiny on the sky, supposing it's not as big as the moon, supposing it's tiny even compared to the moon, so that you actually can't see that you had two dots, or that you had those funny shapes, or that you had a ring. What do you see? Because you don't see the shapes, but you do see that you got more light, right? Because before, the light came to you only one way, and then it came to you from different paths, and then came to you from all these different paths. So because you're getting many, many different pictures of it from all these different paths, it's going to look brighter. So you can't really tell that it's this, or it's a circle, or it's this again. But you can tell that it was faint, and then it got very bright when you got the full circle, and then it got faint again. Okay, so we call that micro lensing. Strong lensing is when you can see the two different images, and the micro lensing is when everything is too small for us to see that there's many images, but you can count that you got more light. It's brighter. So that's our way for looking for objects that are making the light bend. Yeah, because remember, we're not seeing the light from the lens. We're still seeing the light of the background object, whose light is taking different paths to us. But it's doing that because there was something in between. So we can figure out what's in between, right? By how often this happens. But how often this happens will depend on everything had to be lined up nicely. And so you need lots of lenses, lots of dark matter, black hole, things that are perfectly lined up for this to happen at all. And so by trying to measure how frequently by watching a star, it suddenly gets bright. By watching how frequently that happens, we can figure out how likely it is that things got lined up. And so we can figure out how many things there must be for them to be lined up this often. And so that's a game that was played in the 90s. And it was played at Penn. So the guy who had this big survey to do this, it was called, there's a field with many weird names. So the dark matter particle that people looked for, that was low mass, they called it a WIMP, a weakly interacting massive particle, okay? And so when people said, well, who knows, why should it be a tiny dark matter particle? Why couldn't it be stuff like black holes doing the lensing? They said, what are black holes? So they said, those are machos, massive, compact halo objects, all right? And so at Penn in the 90s, they did this survey to look for machos, to look for this happening. Okay? So it's a big computer science problem. You look at the sky every night, you're looking at the same patch of sky, like you look towards the center of our galaxy, and you watch to see any stars that changed, which really means you took a picture tonight, you take a picture tomorrow night, you subtract the two pictures, and anything that changed, you say, oh, let me check if it's one of these things. Now, stars change for all kinds of reasons. You have to account for that. Here, we're lucky. There's this very precise pattern of how it gets bright, how you start getting more and more light, and then you get lots, and then it gets faint again. So there's a very precise pattern for this. So we can look for that. And so we can tell this was because of the lensing rather than because it's a star that's flashing on and off or whatever. Yeah, so we can do that. All right. From doing that, we also know that, for it to get bright and faint again will depend on what's doing the lensing. And so if the lens is a big thing with a lot of mass, it's going to bend the light a lot. And so there'll be a pretty long time where things are lined up, where the light's being bent, where we're getting more light because of the lensing, and it gets bright and then faint again. So it might take weeks to get bright and faint again. If it's smaller mass, then it might take days to get bright and faint again. If it's smaller still, it might take hours to get bright and faint again. So when they did the experiment, they looked at the sky about once a week. When they did that, then they said, okay, we saw this happen, but not enough times for the things that we saw to be all the dark matter. But because they were looking once a week, the things that they could measure were things that were about the mass of a star, the sun, or a little bit less. They could not look at smaller. Okay? And no one has redone the experiment to look on scales of an hour, or scales of minutes, or scales of seconds, for this thing to suddenly get bright. Okay? So that's going to be the way we're going to look for little guys, is by watching stars suddenly get bright and faint again, but with this very characteristic way, because of this effect. Okay? Because of the micro lensing. But there's going to be a wrinkle that I'll come back to later, okay? about this idea. Okay, this is a little more detail about that. This is to show you these things. We really do see these Einstein rings in the sky. They're beautiful. You can kind of see that, you know, this is almost the image of a galaxy. That's the galaxy on the other side. There's multiple images. So the light really did come from different places. And you're going to see many more of these because the James Webb Space Telescope is looking at stuff that's really far away, which means it's much more likely that there's stuff in between that got perfectly lined up. And so we see the most distant galaxies, in fact, because of this effect. In that case, those massive galaxies, they got lensed strongly. So we really do see the full ring. Whereas the stuff that we were doing to find machos, the gravitational lensing is much smaller, so we can't see the full ring. We can't resolve it, so we can just see the total light. Okay. So this is more, right, about gets bright and then gets faint. Okay, but there's not enough, at least in the black holes or in the lenses that are like this massive stars, to do this. So it's got to be less massive. Okay. How do we make less massive black holes? And so this is where we start thinking about other ways than making them from stars. The idea is the following. So you start out with our universe today. And if we look at our universe today, then it's got stuff in it, matter, and it's got light in it. But when I walk around in the universe, then we were super lucky, right? It was a nice warm fall. So it was nice to feel the sun on my skin, right? But it's not like when I walk around, I'm being buffeted by the photons, right? It's not like I'm hit by them, because there's just not a lot of them. Right? They're all low energy. It's not a big deal. So we say that today, we care more not about the light, but we care more about the matter in the universe. We say the universe is matter dominated. Now, we think the universe is expanding. I mean, we know, we measure that the universe is expanding. So that means there was a time when the universe was smaller. And so let's think about all the stuff in the universe. All the stuff in the universe, when the universe was smaller, was packed into a smaller region. So the density was higher. Same stuff, smaller volume. So 1 over the volume is how dense things are. But with light, we can ask, how much energy do we have in light? Sorry, maybe I should do this first with matter. How much energy do I have in matter? Well, E equals mc squared. I take all the matter, multiply by c squared. That's the total matter. Divide by the volume. That's the energy density of matter. Mass divided by volume. What's the energy density in light? Well, I take all the light particles, add up all their energies, and divide by the same volume. if we do that, then today it turns out that the energy density in light is like 1/1,000,000th of the energy density in matter. That's why we don't care about the light, we care about the matter. Okay? Everything is matter today. But the energy of light depends on its wavelength. Shorter wavelength, more energy. X-rays, more energy than radio. And so when the universe was smaller, has the same light in it, but all the waves are shorter because everything was shorter. So if you want to think of it, you can think of it as you had a bunch of light, and as the universe expanded, the waves, the wavelength of the light all got stretched. And so the light lost energy. Okay? But it's the same particles of light. So that means that the energy density of light changes because the volume changed, just like for particles, but also changes because the wavelength gets stretched. So light changes worse, changes more than matter, because there's two effects for the light: the stretching of its wavelength and the fact that the number of particles is the same number of particles, they're just further apart as the universe expands. Okay? So that means that there was a time, if we imagine when the universe was tiny, there was a time when the energy in light was kind of similar to the energy in matter. And so let me try and make that a more concrete statement. Yeah. Right now, we think we know what the light is like, right? We know how much light there is. When the universe was 100 times smaller than it is today, the light, the wavelength was all shorter, so the light had more energy. If I took a cup of water and I put it out and I just held it out in space, it would be, the energy of the light would be enough to make it boil. It would be hot enough to boil water. And so it's a real thing. Yeah, it really is more energetic when the universe is younger. So now let's go younger, younger, younger. Not when it's 100 times smaller than today, 1,000 times smaller, a gazillion times smaller than today. Then for sure, the light matters much more than the matter matters. Yeah? Because all the wavelengths are going to be super short. So everything's going to be light. And so let there be light is the right picture, right? When the universe was young, it was all light. Okay. So this is trying to show that picture. It's trying to show as, if this is today, then what's the density in light compared to matter? Let's not worry about the green curve for now. And so there's much less light than matter. But in the past, there was, the density of matter was bigger because the volume was smaller, but the density of radiation was higher, both, because of both these effects, right? And so that means that if I go really, really early, then everything is radiation compared to matter. Everything is radiation. Okay. So the neat thing about this is the following. Supposing at this time, because there was a time when the energy densities were equal. Suppose at this time, I took all my light and I turned it into black holes. However, right? So we'll get to however in a second. Supposing I turned it all into black holes. Well, black holes, they're like particles. They're like matter. And that means from that time on, this energy doesn't decrease like this. From that time on, the energy will decrease like matter particles. Just the black holes will get further from one another, but they'll still be there. And that means that today, I will have a lot more stuff, a lot more matter in the universe. Because I took the light that would have decayed away, but I stored it in black holes to survive by the present. Does that make sense? Yeah? Yeah.
Whether about energy balance over time, energy initially you're saying would have been in the light.
Yes.
Versus the matter. Was it being transferred to matter as the light was extending its wavelength, or was it going into black holes, or where was the energy going?
It's lost. In the usual picture, it's lost. It's not conserved. Yeah. So in the usual picture, the decay of radiation is gone. There's energy conservation only in the sense that if you ran the clock back, you get it back. But otherwise it's gone. Yeah. And so, yeah. And so really this is a game of saying you're taking stuff that you would have lost and you're storing it away, right? If you could do this, this would be a way to have more matter. Because you took the fact that you have a bunch of this stuff and you turned it into matter. And once it's matter, it doesn't decay as quickly. Okay. So then you'd say, okay, that's great, but it's crazy, right? You got to make black holes out of light. Any way of doing that, it must be super rare, right? So even if you're going to say, oh, all right, I'll let you do it, I got to make sure it doesn't happen all the time. And that's fine, right? Because supposing I did this when the universe was 100 years old. If I did this when the universe was 100 years old, and I turned all the light in the universe into black holes, then it would survive to the present. And, if there's 10 to the 10, so if there's 1,000,000 times more energy in the radiation, then there would be than the matter, there would be 1,000,000 times more energy in the radiation now, in the black holes now. So too much would survive. And so the earlier I do this in the universe's history, the less I need to do this. Yeah, so if I'm going to do it late, then I've got to turn all the photons into black holes. But if I turn it here, I've got to turn 1 in 1,000,000 photons into black holes. And if I do this super early, it can be a tiny, tiny, tiny fraction that survives. And that's going to be enough. So that's the beauty of this idea, is that you say it's crazy. It should be so rare, so unusual if it's going to happen at all. And that's just fine. In fact, that's good. Yeah, you don't want it to be off. And you just push it back earlier and earlier.
Yes.
The island is on too.
Okay, so that's the idea, all right? So this is going through and saying, for this to work at all, we do need places in the universe where there were a few more particles of light than others, and those moved together so that they got into a concentrated enough region that you did make a black hole from which they then couldn't escape. Right? So if the light was perfectly smooth, this wouldn't happen. So it's got to be regions where there was just a little bit more. And because there was a little bit more, there ended up being enough particles of light that all moved in the same direction. Now they're too concentrated. And so now they've made a black hole and they can't escape. Okay? It's got to be super rare. But so long as we see that the universe is a little lumpy, then we can imagine that was those little lumps that will have turned into, some of them, very rarely, will have turned into a black hole. And that we can then start asking, can those things survive to the present, right? So that now we're at the question of, okay, I needed to do this very early in the universe's history so that I don't, because it's a very rare thing. But that means that there are tiny, tiny patches of the universe that are turning into black holes. And so they're probably not very massive black holes. And so I've got to worry about whether they survived the next 13.5 billion years to the present. Okay, so that's the picture. Let's go through, right? So this is saying, you know, a tiny fraction has to make the black holes. And so it's an old idea. All right, this is a nice quote by Churchill. This idea goes back to Hawking and to Zeldovich, right? Who both said this at about the same time, that you should be able to make black holes out of light. Okay. And then it was kind of forgotten and people didn't work on it. And about every 10 years, people would come back to this idea and think a little bit more about it. But there's a sort of a bunch of things that have happened recently that have made people get excited about this. The biggest one is that for 50 years, we've looked for dark matter and not seen anything. And so this one is a kind of natural thing to look for. Okay? So let's think a little bit about what these things will look like. So a black hole that is the same mass as our sun. So our sun is 100 times bigger than Earth, 600,000 kilometers across. So if you took that sun and you squeezed it into something that was the size of Westchester, 3 kilometers, that would be a black hole. Okay, so super dense. So instead of that, supposing we wanted one that had the same mass as Earth, then that thing would be smaller. A black hole that's the mass of Earth would be the size of a dime. A black hole that is the mass of an asteroid would be a proton. Tiny, tiny, tiny. Okay? And so the micro lensing that we talked about before, well, that big, nice Einstein ring that we looked at before, that's made by something like this, where it was something that was about 1 billion times the mass of the sun that was bending the light. The black holes that we've looked at for the Macho project, they're like the mass of the sun. The black holes that merge to make the gravity waves that we can measure, they're like the mass of the sun, 30 times the mass of the sun. So they're these guys. Now we're talking about the ones that are like a dime or smaller. They're still supermassive, but they're tiny. Tiny is good, right? Because tiny means there've got to be a lot of them, because they've still got to make up all the dark matter. And so if you go through the numbers, tiny means there's going to be a few in our solar system. And so now you have to worry about, well, if there's a few in our solar system, what happens if they hit us? Right? So you want them to be rare, but you want there to be enough of them to be the dark matter. And so let's go through a little bit of what they might be, right? So this one is if they are the mass of an asteroid. And so this is just to set the scale, right? If they're the mass of an asteroid, they're not going to be this big. If they're the mass of an asteroid, it's going to be all this mass in the size of an atom. And so what if one of these things came through Earth? So if an asteroid came through Earth, that's a big deal, right? That hits things and there's a big crater and stuff gets blown up into the atmosphere and we'd worry about whether there's a nuclear winter. Right? Well, not nuclear, but yeah. Okay, so that same mass if it's the size of an atom, comes right through this room and doesn't hit anything. Okay. And so, would we notice? Yeah. So it turns out that Earth has detectors for earthquakes. And so the earthquake detectors, what do? Well, they're basically, you know, earthquake goes off, Earth shakes, waves go out in different directions, and detectors elsewhere start to ring. And then what we do is we say, oh, that one rang before that one. And so we reconstruct where the earthquake started. And so we figure out what was the epicenter from timing when all the detectors started ringing. And when we do that, we trace back to an instant in a position in space, right? That's where the earthquake was. Here, you're going to have something that's kind of like an earthquake, because at the end of the day, you do have Mount Everest plunging through, right? It just didn't hit anything, but it is mass. And so it's going to be kind of like an earthquake, because all this mass suddenly just went through. And so the stuff's going to start moving around. But when you try to reconstruct the signal, the earthquake signal, well, this thing just went plummeting through Earth. So it's kind of like a straight line through Earth. And so when you reconstruct the signal, it's not going to reconstruct to a point. There's not going to be an epicenter. There's going to be an epiline, if you want, right? It's going to be this long line that was the source of the earthquake. And so currently, people don't look for these things, right? If it's something reconstructed to a line, they'll be like, oh, you know, one of the machines on the blink, right? And that's why we got this crazy thing. Let's throw it away. So now this is saying maybe we should pay attention, right, to the things that don't make sense, that we just throw away otherwise. Okay, so people have done the numbers, right, of you know, how likely it is. I'll come back to the lifetimes, right? So here are some things, right? So the black holes, not the mass of the sun, but we're interested in the ones that are more like the mass of an asteroid. Okay, and so we're interested in other ways we might see them. So I said one way is an earthquake that reconstructs to this weird shape. So if one went through Earth, it would do that, but maybe it would go, what if it went through the moon? What if it went through Mars? So let's look at a couple of things. So people have studied craters that these guys would leave. So before we talked about what happens to earthquakes on Earth, right? But we can think about a normal asteroid that hits a surface, and the asteroid is like a rock, and it's hitting a surface that's like a rock. And so what it does is it buries in, but not super deep. If you have two things that are kind of the same density, you'll make an impact crater, but it won't be the same kind of impact crater as if the thing coming through was super dense. The thing coming through that's super dense will drill much deeper. In fact, when I talked about Earth, I said we'll probably just go right through. But it's clear that if there is a kind of crater, this crater is going to chuck stuff up kind of straight up, whereas this crater is going to chuck stuff up in different directions. It's kind of going to hit and splat, whereas the other guy is going through, and so stuff is being chucked out this way. And so the shape of the crater, how the stuff got piled up around the crater, tells you something about what the thing that made the crater was made of. Now, we can't do this here on Earth because we have atmosphere and we have volcanic activity and tectonics, and they just change Earth's surface all the time. And so we don't have a record of all the craters that have hit Earth. But we do on the moon, because it doesn't have an atmosphere, and we do count craters, right? That's one of the ways from counting the craters and saying, you know, how many big, how many small, we know how many things hit moon, what hit moon probably hit Earth. So we know that, you know, a lot of Earth's water was probably brought to us by asteroids hitting, by comets hitting. Right? And so we know that this happened a lot. But we've never paid that much attention to the shapes of the craters. And so this is saying maybe we should. Now, yeah, we'll have to worry about the crater shape that you make. This is the easy case, right? Where they came straight down. But maybe it came in at an angle. And if it went in at an angle, then it's going to shoot stuff out. But again, it'll be different here compared to here. And so people are beginning to think about studying the shapes of the craters on the moon and then on Mars. No atmosphere. And so there's a hope that there's a memory there. So that's another crazy way to look for these things. Yeah. Another question people have asked is, if I have one of these black holes that gets caught by the cloud that made our sun. So the sun is forming, but there's a little black hole in the middle. A black hole the mass of Mount Everest. Does it change what happens to the sun? Well, it's so tiny, it doesn't. So the sun cooks just the same as it would have anyway. But the black hole does grow because it's eating what's nearby. And so it will get more massive. But it's starting out the mass of an asteroid compared to the mass of the sun. So it was 10 to the minus 20s, was tiny, tiny, tiny. But over 4 billion years, it gets bigger. And so eventually, so it gets bigger because it's eating stuff, right? It's eating the core of the sun. And so gradually, we can think about the energy that the sun makes from fusion versus the energy that the sun makes because the black hole is growing, as the stuff falls onto the black hole. And we can ask, when do those balance? When does the fact that the black hole is growing dominate over the fusion energy? And so that turns out to be, for a star like the sun, about when the sun becomes a red giant. So it doesn't change much of stellar evolution for a star like the sun, but it will once it's off, once it starts cooking helium instead of hydrogen. And so that's made people think about, well, when we look at stars that are becoming red giants, are there weird stragglers that we can't explain? There's the normal population of red giants, and then there'll be the few that caught one of these guys. And can we study those? So it's another of these big data things. We're going to have data, we're going to get pretty exquisite measurements of billions of stars. Currently, billions of stars in our galaxy. But in the next generation, called the Roman satellite, which should launch in about 3 years or so. It's NASA, so maybe 4, maybe 10. No, don't quote me. But it will launch, and it will resolve stars for the nearest about 100 galaxies. And so then we can start asking, okay, some of those stars are kind of like red giant stars, but are they like weird? Are they not quite where they're supposed to be? And then we can start asking, are they consistent? Because people are running stellar evolution models with black holes in the core. For anyone who's run a stellar evolution model, it's a beautiful problem. It's a star is a balance between gravity and energy. And now all you're doing is you're adding a point in the middle that's like an energy sink, which is the black hole that's getting bigger. But otherwise, it's the same argument. It's the pressure going out, you know, gravity pulling in and the pressure going out. But now a slightly different boundary in the core. And that boundary is growing. It's a beautiful problem. And people have begun looking at it. And so So the idea is that what's going to happen is that the central structure of a star will change, right? As the black hole grows. And so you will start, before you had fusion where you had energy going out, now you have stuff trying to come in to make your black hole. And you're going to change the region in the star, which is boiling, and the region in the star where you just have radiation going out. Yeah. And so you will change stellar structure, and we might be able to tell that. And so here's the thing, here's the statement, right? That the sun would look pretty much the same if there was a black hole that was like the millionth the mass of the sun in its core. It wouldn't look any different. It started out like an asteroid, so and it grew to being a millionth, and we still wouldn't notice it until later. Okay. All right. Another way we might find these guys. So the James Webb Space Telescope has looked in the sky and has seen galaxies that seem to be more formed than we were expecting, more massive than we were expecting. And that's got a lot of press. Yeah. And so one of the reasons people got excited about these kinds of primordial black holes is that these galaxies are almost at a time when there should not have been enough time to make lots of stellar evolved black holes. And so one idea is that maybe back then, these black holes, which had been formed when the universe was super young, you should think of those black holes as plankton. And you should think of, let's say, the first stellar mass black hole is kind of like the whale, and it's going through and it just sweeps up the plankton. And so it grows much more than it would otherwise, grows much faster. And so you make a much more massive seed around which to grow a big galaxy, much more efficient. And this would help explain the James Webb Space Telescope. Yeah. And so this is one of the reasons people have got in this current iteration of black holes from light. This is one of the big reasons. Yeah, is saying that it helps explain a wide variety of things, right? Structure formation when the universe was super young, and dark matter today. Okay. So the idea is, that now it could be that the Webb Space Telescope is beginning to see the structures that were seeded by these primordial black holes. One last idea, and then I'm done, right? Because it's late. So back to the gravitational lensing. Right? So can we do that? And so I said with the gravitational lensing, we had to worry about the fact that, well, if it's a star like, or if it's a thing like the sun doing the lensing, then that thing will last for a while. And I said weeks or days or hours. So if the black hole is the mass of an asteroid, it's the size of a proton, then it's like quick. Okay. So it's going to be hard to see. But people tried to do this anyway. Okay? They tried to say, well, something will get bright and faint. Let's monitor using telescopes for stars that suddenly flash bright and get faint again. And then they realized they've got to be careful, because one of the things that we do when we think about lensing is we draw these rays, right? How the rays travel. But now, if your black hole, if your lens is the size of a proton, if the wave is longer than the proton, the wave is longer than the thing that's making it bend, it doesn't see the thing that's making it bend. An analogy. So I bike to work. I bike to work at Penn. I live near the Art Museum. When I bike, there's like potholes everywhere. Okay. And so for me, it's a pain because those potholes are about the size of my bike wheel. or the spacing between my bike wheels. And so I feel them. I think it's impossible that the mayor doesn't notice, right? But the mayor is riding a stretch limo. Mayor, the front wheel goes in, back wheel still out. Those bumps and wiggles in the road, they're not there. Mayor doesn't know there's an issue. Yeah. So same kind of thing here is that the light, if it's long compared to the black hole that's trying to make it bend, the light doesn't notice. Or it doesn't notice in the normal way we think about light. And so we can't think about the light being bent and being focused and making a bright image or a faint image. So we call that the geometric optics limit. And geometrical optics doesn't work anymore when the wavelength of light is the same size as the thing it's trying, that it's interacting with. And so there's beautiful problems to be done there. What happens when you're in the wave optics part of light, where the thing making the bending is the size of the light itself? And so people realize we've got to be careful in this problem for that, which means we can't do this with optical light, but we could with X-rays. X-rays are shorter. Or with gamma rays, they're even shorter. And so we have to look for lensed gamma ray signals rather than optical or radio. And then we should be able to do this. But it's still hard, right? Because you've got to be super lucky. Everything's got to be lined up, right? And then it's going to be these gamma rays. So it's science fiction, okay? And then it's going to last for a short time. So what do you do? And so the final idea is this thing called parallax lensing. So here the idea is that instead of one telescope that's looking at stars and trying to see which one blinked on and off, because the lens got lined up. Instead of doing that, you say, well, let me have two satellites, one on either side of the Earth. And if I still thought the geometric optics way, then I would say, well, this lens is so small that when it's perfectly lined up with the source and here, it's not perfectly lined up with this guy over here. And so that means this guy blinks on and off, and this guy hasn't. And then I'll have to wait before that's lined up. And then this one will blink on and off. And so when they blink on and off in concert, that's how I know it happened. That one of these primordial black holes hit the lens. So that's called parallax lens. So I thought this was science fiction. So I was at a conference a few months ago, and I talked about this idea. And someone came up to talk to me, said that he's with the Chinese space agency. And he said they have lots of gamma ray monitoring satellites for other reasons, right? And but they can monitor the gamma rays coming from the sky, and they have more than one satellite doing this, so they could start doing this thing, right? And looking for the signal. And so that's parallax lensing. So that's different from the micro lensing or the macro lensing, but parallax lensing. Okay, so the quick summary is primordial black holes could be the dark matter, and they would have to form from radiation. We talked about how a few ways we might see them, but I didn't talk about whether or not they evaporate, whether they would survive. Okay, so let me cycle back to that. So if we had a black hole that was the mass of Earth, so there's a big fight in the field at the moment, right? So Hawking said that black holes should be able to evaporate. And the fight is, you should think of a black hole as a box in which stuff was put. And now the question is, when stuff comes out of the box, do you know what had been put inside? And so the idea had been that a black hole is it has no information about how it formed. So the jargon is black holes have no hair. So they just have a mass. They have an electric charge, maybe, but probably not, and they spin. And that's it. And then whether you made them by throwing hydrogen in or throwing gold in, or Bitcoin or whatever, right? It's gone, right? You can't tell the difference. And then when it evaporates, you have no memory of what went inside. That's what Hawking thought, right? What comes out has no memory of what went in. We now think that's wrong, right? So we think that there is a memory of what went in. And so that's a whole different story, okay? That when they evaporate, there was a breakthrough not quite 5 years ago saying we do think the information comes back out. It'll be difficult to get, but it comes back out. Okay, so that means we do think they evaporate, okay? And the energy comes back out. And so we can ask how long before they evaporate, and it's very slow. So a black hole that is the mass of the Earth, the one that would be the size of a dime, would take a gazillion years to evaporate. So for the, we really don't care. But for a black hole that is the size of Mount Everest, the mass of Mount Everest, then it would take about 1 billion times the age of the universe. So those guys would still be around. Okay. The kinds of, the Great Pyramid, that would evaporate in 300,000 years. So if this was made when the universe was young, it's now gone. And so that's why I was talking about asteroid mass black holes, and not lighter and not heavier, because the ones that are like the mass of a planet or the mass of a star, we know there's not enough of those. We've seen those signals. So there's like this gap, this sweet spot, the Goldilocks black holes that are about the mass of an asteroid. That's like the gap where it could be, yeah, where the dark matter could be those. And there could be enough of them to be interesting. And those guys, they will not have evaporated by the present time. Just about. That said, now that we understand more about how black holes evaporate, we can also ask the question, the process of evaporation is a slightly weird thing, because you're taking, let's take something that was like the mass of Earth and evaporates. So it's the size of a dime, and it's evaporating. So as it evaporates, it's going to get smaller and smaller and smaller. Eventually, it's going to be small that I shouldn't be able to think of it like a dime or like a, I have to think of it as using quantum mechanics, because it's small like an atom. And once I'm in that regime, it's not clear that we can keep thinking about it like a particle that's gradually getting less and less massive. There's going to be eventually, and a crude number will be, once about half of it is evaporated, I've got to be careful about what I assume about the other half, whether the same rules apply. And the models that people currently have, they say, if anything, they're going to take longer to evaporate than we think, not shorter. And so it could be that if there are primordial black holes, then those black holes, they could be much lighter and still survive. They'll have started to evaporate, but they're still around. Whereas currently we assume that they're gone. Yeah. but now we're in the science fiction of making black holes out of light and the science fiction of how they evaporate and the science fiction of how much energy gets out, right? And so that's a lot of crazy ideas for one night. So I should stop there. Yeah. Go ahead.
I guess I'm just wondering, like, I'm trying to add up the math problem here of like, if they're super rare, then how do we see them as the potentially 95% of the mass of the universe? Like, how is that? I guess I'm just, that doesn't line up in my mind.
It's a good question. It's a good question.
How does it rise, all of that?
Right. So in this case, so there's two ways to answer that. So one way to answer that is to say, like, where we are on Earth is super unusual. So it's super dense on Earth compared to the rest of the universe. So when we say we want to make more stuff to account for how much stuff we think there is in the universe, we have to remember that actually the universe is a really empty place. And so it turns out that if everything were the mass of an asteroid, then there would be a few of these in our solar system. So that's tons in our galaxy. Yeah. And so that's why this analogy of plankton with whales is a good one, right? So there's a lot of them, but they're all negligible. So they're going to be really hard to find. But negligible, so it's a bit weird to be talking about plankton but a few per solar system, right? But when you say a few per solar system means a gazillion per galaxy, then there's a lot of. But now, because they're so small, it's very difficult for things to get lined up perfectly to actually see them. Or they're so small, it's very difficult for them to actually collide with something. Because, you know, even though they're abundant, they're tiny. And so the chance of collision is tiny. Yeah.
So to make a black hole, you need mass, right? Well,
okay.
let me finish my question.
Yes.
You
Yeah.
need mass. The rest mass of a photon is 0, right?
Right.
Relativistic mass, though, may be significant.
Yes.
But does that act the same as mass?
Yes. Good question. Right. So that was the original thing that Hawking and Zeldovich worried about. Right. Is that so in Einstein's relativity, what gravitates is energy, not mass. Yeah. So the thing that makes gravity is the total energy. And so from that point of view, photons, even though they don't have mass, because they have energy, if you put enough energy in a small enough patch, you can make a black hole. Yeah, so now there are subtleties. Okay, so if I start putting lots of photons in a small region, those photons can make electrons and positrons. In fact, that's one of the mechanisms for making a black hole evaporate in the first place, is making particles and antiparticles. And so people have worried about whether the process of trying to turn photons into black holes gets shut off by the fact that you can make particles and antiparticles along the way. And so it doesn't make the black hole. But currently, people think that it will go all the way. That yes, you will make 2 particles of light into matter and antimatter, but they're right next to each other and they will meet each other and they will turn back into light. And so it will just keep doing this. And because it didn't go away, you will make your black hole. It didn't disperse. Okay. But there's another neat idea. Okay. The other neat idea is, so I said black holes we think have no hair. So they have a mass, they have a spin, they might have an electric charge. Mostly we think they don't have electric charge because mostly we think they're pretty massive. And if you got a lot of mass, it was probably the electric charges canceled out. But now let's think about the super early universe when this was supposed to have happened. So this is supposed to have happened, not when not even when matter as we know it existed, right? Because it was so hot that the light could make matter, the matter could make light. You're going back and forth all the time. So you're back in the time when in physics, we think that currently we think of there being four forces: gravity, electromagnetism, the strong force and the weak force. We think when the universe was hot, there was a time when electromagnetism was the same as the weak force. And when it was even hotter, the strong force, the weak force, and electromagnetism, they were all the same. There were Nobel Prizes for realizing each of these things. And no one's been able to figure out how to make gravity the same as the others. Yeah, but there's this vision, right? That early in the universe, they were all the same. But let's stick with what we know. The gravity is whatever, but the other three, we can think about the time when the strong force becomes different from the weak and the electromagnetic. So there was like a phase transition when the universe changed from, from being just gravity and the other to gravity, the strong force, and the other two. At that time, quarks were in the cosmos all over the place. Quarks come with color, right? And so now we should imagine that the early universe was frothing, light was turning into quarks, quarks back into light. But some places in the universe, I had this picture where I said that the universe was not completely uniform. This is a picture of the cosmic background radiation, which is just the photons. There are some places where there are more and less in our universe today. But the early universe was like this. There will have been hot places and cold places. Hotter by a little bit, colder by a little bit. But in the super early universe, these same differences could be where you made more red quarks or blue quarks or green quarks. So you could have had not just perturbations in how many photons, but whether those photons happen to make one kind of quark or another. And if that happens, then you will make black holes out of red quarks rather than green. And so what happens when those evaporate? What happens when a red quark black hole, because now the black holes have color, right? So they have a little more information. I guess they dye the hair they're not supposed to have. I don't know, right? Yeah. But so people have started thinking about that problem. So there's lots of kind of beautiful physics problems to think about that you wouldn't have thought about before, just because this is such a crazy idea, right? Yeah.
Not particularly crazy because the conditions are so extreme.
Yes.
But a question along that line is, if we're thinking that light can be essentially compressed into black holes this way, what does that tell us about the time period for the cosmic inflation?
Yes. So the current ideas are this happens just at the end of inflation. Okay, so that's sort of the leading way to do this. So this phase transition that I talked about is the end of inflation, and at the end of inflation is this kind of thing happening. So that's the place where they're doing not where they're doing. That's the place where people are building models for.
It would work, because once you get much beyond that, it's happening so fast that how are you going to be able to compress them back dense into that?
Yeah, I mean, so maybe it's worth drawing a picture, right? So let's pretend that the universe is totally smooth, and I'm going to draw a circle here, okay, around that center. And so now, light has a finite speed, right? So I first want to ask, the photons that started out here, where are they after 1 second? After 1 second, some went this way, some went this way, some went this way, right? And so they've gone 1 light second away, 2 light seconds away, 3, 4, 5, 6, okay? from here, there were photons that were going out 1 light second, 2 light seconds, 3 light seconds. So now I can imagine the universe, it started out and all the photons are released from everywhere. So I just imagine these circles going up that tell me where this guy's photons got, where this guy's photons got, where this guy's photons got. Okay? And for each of these, I can ask, well, so after 1 second, what are the photons? So after 1 second, there's the radius, which is 1 light second around here. There are its photons, but there are also photons from outside that have come in. Right? There are photons from in that have gone out. There are photons from out that have come in. And so I can add up as time goes on. You know, the photons that are inside this patch are a mix of the ones that started out here and the ones from outside. And so I can just ask. Supposing now I arrange so that the universe wasn't perfectly smooth. Because if it was perfectly smooth, it doesn't matter, right? What came and went. But supposing now I imagine that I had a patch of the universe where I had extra photons there and none here. And so these photons, you know, they went out in that direction, but they also went this way. And the same with these. And so there was nothing here to get lost. But now I have all these photons that were initially spread out in this shed that have now ended up here. And maybe that's enough to make a black hole.
Well, this explains why we have to be at the end of inflation, because during inflation, it's going too fast.
Yeah, so everything's
It's actually technically, it's not as far as the photons concerned, as far as everything around is going faster than light.
That's right. That's right. Yeah. So the expansion is super fast. But this is like a very nitty-gritty way of saying the photons have to move. And so now you can imagine that there was some pattern that gets transformed, and you have to get, you know, lucky configurations that are going to be just right to concentrate all the photons at the same time so that you can make something. Right? And so that's the end. Thank you. So this was really further out. Yeah. Thanks for the fish. Thank you.
Thank you once again for coming. And for everybody else, have a great month, and we look forward to seeing everybody at the party. If you're even thinking of coming, shoot me or any of the execs an email so we can get roughly the size of the stampede that the Four Iron Hill Brewery is going to be expecting. Thanks again.
I'm so glad I'm a pharmacologist.
Well,
Very cool.
That's a crazy idea.
yeah. It's like doing the physics of what's happening in black. Essentially, they're the same, you have the same.
You have Elvis?
We have no idea why.
But they all kind of.
This is Parker.
There's Elvis,
Yeah.
and that's Polly.
Oh, Polly's over there. Oh, okay, now I see her stripes.
And Elliot just left, probably went to bed, getting it ready for me.
Yeah. So Parker's here. Jack was on my lap for a while. We started off with Crystal. Now I'm getting bitten. Oh, you're mean. You're such a little meanie. 7 pounds of mean.
7 pounds? Oh, yeah. This one's
Yeah.
the smallest at 12.
Now the Crystal's about 8.5. And then the guys